Welcome, this is 48E video 3, and we're going to talk now about the possibility of using these kinematic equations for three-dimensional problems without writing them down as components. So we talk about vector equations for 2 dimensions or 3-dimensional motion. And what we say is we can write the equations of motion in vector form. So here's the way we've been doing it so far. We've said, okay, work in one axis. This is the equation that works for all the x-axis materials, and we can use the same equation for the y-axis materials, or we could use the same equation for the z-axis materials, but we can't mix them. I can't use the initial velocity in the x-axis with the final velocity in the y-axis. They don't go together. But here's a vector equation. I can see it's vectors because it has the arrows above, and this is saying that the vector VF, 3-dimensional, is equal to the vector VI, 3-dimensional, plus the 3-dimensional vector for A times the time. And if you look, you see that they're the same equation form. It's just that traditionally we used scalar values on a given vector and a given axis, and now we're using the IJK vector form. So it's really quite interesting. I can show you this graphically, and we can see here that what we have is take this equation VF equals VI plus A delta T. I can only show my diagram in 2 dimensions, but believe me, this is working in 3 dimensions. What I'm saying is that my VF, my answer if you like, is given by the vector sum of the initial velocity vector plus the vector, which is the vector acceleration multiplied by the time, the delta t. And I can do the same thing for another equation. Rather than saying delta x, they tend to say delta r. It's just style, but they say the vector displacement is equal to the initial velocity vector times the time interval plus a half times the acceleration vector times the time interval squared. And for this third diagram, I'm using the same equation as I did in the middle diagram. I'm just using it in a special case. What I'm saying is that for projectile motion, I know that my acceleration is 0I because there's no component of acceleration in free fall horizontally, plus minus 10J because it's minus 10 meters per second squared and it's pointing downwards, plus 0K meters per second squared, and that simplifies to to 0I minus 10J plus 0K meters per second squared. Cool. So the message is we can use, in certain cases, we can use IJK notation on some of these. Let's try one. A particle has an initial velocity of that. I could draw it to scale, but I don't need to. I'm just going to draw it. And this is going to be 3I minus 2J plus 4K meters per second. And this is my VI. It has an acceleration of minus 2 plus 4 minus 6 meters per second squared. So let's just draw this acceleration down here and say this is minus 2I plus 4J minus 6K meters per second squared. And then we ask ourselves, well, what will that do? It will change that velocity as time passes. And then what is the vector velocity after 6 seconds? So I'm going to draw this in kind of like that. So here's my delta t is equal to 6 seconds. And I can imagine my velocity after 6 seconds pointing down something like this. This is going to be v final. And I say this is equal to, I don't know. So I visualized it. Now let's make a list. So I say, well, my vi is equal to, rather than a scalar value, I'm going to put down a vector value. 3i minus 2j plus 4k meters per second. And then I say, well, okay, my acceleration was given by minus 2i plus 4j minus 6k meters per second squared. I know my time is delta t. It equals, we said 6 seconds. And I want to find my VF. And these, of course, well, that's a vector, so let's mark it as such. That's a vector. Times a scalar, there's a vector, and I don't know what that is. Remember, the diagram is just schematic. The direction minus 2i plus 4j minus 6k is not down the page. It's just schematically drawn that way. So I say, well, the equation I'm going to use is VF is equal to VI plus A delta T, and I just need a way of laying this out so I can do these additions. So I make a table. I go I, J, K. This way I can keep track. And so I do a grid system. And I say, what do I need to do? Oh, VI. Let's do VI first. I look at the side. I say, well, that's a plus 3. That's a minus 2. And that's a plus 4. And then I got to add. And then A delta T. Well, my A is here. And my delta T is there. And I'm multiplying them together. So 6 times minus 2 is minus 12. And 6 times plus 4 is plus 24. And 6 times minus 6 is minus 36. So this was A delta T. And so I'm going to try and find my VF. Well, my VF is got by adding these two guys together. So I go minus 9 minus 2 and 20 plus 24 is plus 22, and then plus 4 and minus 36 is minus 32. So I would write down my answer as minus 9i plus 22j minus 32k. It's going to be meters per second. I like to put these things in parentheses and put a nice box around it. It's nice to remember to do your little hats on top of your unit vectors. And there we have the answer. Minus 9 plus 22 minus 32. There's that answer. So I think part of it is knowing how to write this thing down efficiently. So I think the actual grid system actually helps me a lot. And having a schematic diagram, it does not have to be literally correct, but it has to be figurative. It has to be able to show you that you have an initial velocity, you have an acceleration, etc. Let's have a look at this next one. A projectile has an initial velocity, so okay, we have an initial velocity plus 5i minus 4j plus 6k. That's going to be meters per second, and this is going to be vi. What is this vector displacement after 3 seconds? So my delta t is equal to 3 seconds. I don't really have as much information explicitly stated, but that's the issue with free fall questions and with projectile motion questions. I got to figure some stuff out. And the first thing I remember is that my acceleration in a projectile is the same as my acceleration in free fall. And this would be 0I, because there's no x component to it, minus 10j, because it's minus 10 pointing downwards, plus 0k meters per second squared. So although it's not said in terms of giving you a vector, the fact that I called it a projectile means that that must be the acceleration. A projectile is 2 or 3 dimensional motion which is in free fall. So the only force acting on it can be that of gravity, so the net acceleration is downwards at minus 10 meters per second squared. And I can visualize now, so now I have some kind of change, and now it's not asking me for, there's my delta t if you like, equals 3 seconds, and now it's not asking me for my final velocity, it's asking me for my displacement. So there's my displacement, and that's a vector. So I can look over here and I can make a list, and I'm going to say, okay, vi is equal to plus 5i minus 4j plus 6k meters per second, and my a, which again was not said explicitly but I know from the physics context, is 0i minus 10j plus 0k meters per second squared, because it's a projectile. And I know my delta t is equal to 3 seconds. So now I want to know my displacement. And what I say is, I say delta x is equal to vi delta t plus 1/2 a delta t squared, my old kinematic equation. This is in vectors though, so it's vector displacement, vector initial velocity, vector acceleration. And again, I need to have a grid, a nice simple system to do sums on these things. So I'm going to do a nice grid system, and the first thing I need to do is I need to have vi times delta t. Well, here's vi at the top and here's delta t, so it's 3 times. 3 times plus 5 is plus 15, and 3 times minus 4 is minus 12, and 3 times plus 6 is plus 18, and that's going to be vi delta t. There's my vi delta t bit done. And then I want to add it to 1/2 a delta t squared. Well, delta t is 3, so 3 3s are 9. 1/2 of 9 is 4.5. So this is like saying 4.5a. And 4.5 times 0 is 0. And 4.5 times minus 10 is minus 45. And 4.5 times 0 is 0. And according to this equation, I need to add these two together. So I add these numbers and I get plus 15i, and then I get minus 45 added to minus 12 is minus 57, minus 57j, and then I get plus 18k meters per meters, and this is my answer. Don't forget, it's a nice point always to get little hats on. And just to satisfy myself, I've got a 15i minus 57 plus, yeah, so there we go. I do write the common mistakes down here, so sometimes if I make a slip when I'm doing it, I'll actually find the answer up there. So to some extent, the little answers up here don't help me that much. Please realize what we have just done. We've done a projectile motion problem on 3 dimensions, and we did it as one process. If we tried to use the I, the J, the K axes independently using components, it would have been a much longer process. This is the wonder of the IJK system. I'd like to do one more thing before we leave, and that's this. I want to look at these equations. So I can easily use this methodology for this guy. It's just adding and subtracting vectors. I can easily do the methodology for this equation because I'm just adding and subtracting vectors. I'm multiplying by a scalar at one point, multiplying by a scalar which is a half. I can do this vector, this equation, because again I'm squaring a scalar, but I'm multiplying it by a vector. I'm multiplying a scalar by a vector, so I can use that one. This equation down here is problematic because it's asking me to square vectors, and so don't expect an equation using this, but these are fair game. There we have it.